There are a few definitions in this, but that's because we haven't done this sort of lab procedure yet. So when you have an acid-base reaction and you're looking at the stoichiometry, it's sort of similar to the dilution math we did yesterday, where you have a concentration of an acid or a base and a known volume, and then you add a volume to the acid or base and solve for the unknown concentration. That's normally what we're going to do. It's called titration, which is a very, very analytical procedure. And what that means, it's very, very, accurate. So we're going, if you can see at the back, we're going to use burettes. So burettes have very good, very accurate calibrations. So much so that they actually cost $92. So you have to be very careful with them. And you can see in the note, this is what they look like. So you can see all the little ticks there on this cartoon burette. And so these calibrations are very accurate. The error in their calibration is very low, which means they are very expensive. Okay? So we are going to, in our lab today, you are going to add, you're going to fill the burette with acid, and then you're going to add base to it. You're going to fill the burette with acid and then have base in the flask and add the acid to it. So usually the acid is the one that's standardized because bases react with water in the air, but it doesn't have to be. It doesn't really matter what you put in the flask and what you put in the burette. Technically, the titrant is what goes in the burette and it's added to the flask until we reach equivalence point or end point. So titration is the lab procedure part. So a standardized solution is a solution that already has a very precisely known concentration. Burette is it looks like a tube that is used to accurately measure the volume of titrant added. So again, depending on what you did in grade 10, you might have done the acid spill lab where you had to add drops until it changed color and you had to build a graph and stuff like that. So you think about those plastic pipettes, how you guys have used them before, counting the number of drops, how hard it is to do that. When you add titrant using a burette, because of the accuracy, then you can get as close to a pH of 7 as possible, okay? So you can even use 1 drop at a time. There is a stopper at the bottom, and the very bottom, the tip part, is very narrow. So be careful with your flask that you don't break that tip, because it helps with adding tiny, tiny amounts so that you can get as close to a neutral pH color as possible. You can do this quantitatively, but digital pH probes are very expensive, so we'll end sort of fragile as well. So what you're going to do in the lab is swirl the flask. So swirling you could bump and then break it and then it doesn't work anymore. So we're just going to visually show pH changes using an indicator and then use that visual determination to calculate unknown concentration. Next year, we will take it a step further and calculate pH as well. So we want a good indicator that has a different color and an acid or base. So again, we're going to use bromothymol blue, which is yellow in an acid, blue in a base. So then what you're going to try to achieve is close to green as you possibly can, maybe slightly yellow. So those of you, when we did the neutralization lab before and you got pea yellow, that's too far. So you want to try to not get that big of a temperature, big of a color change. So one person should be working the stopper. and the other person should be continuously swirling so that you get the best results possible. And what you'll start to notice is the color change will kind of linger. So you'll add a drop and it almost looks like diffusion, and then it will linger, and then all of a sudden go back to what it was. That's your clue. Whoa, I'm close. Okay? So then you're going to even try to go as slowly as possible, add a little bit at a time, and get as close to the slightest color change possible. And when you do these labs, we do 3 trials and take an average because it is qualitative. So sometimes the first trial is the worst, and then you'll know how much has to be added, so then you can kind of be a little bit more careful, okay? So titration, the lab procedure we're going to do, is actually sometimes used because of the accuracy and the precision in the equipment is used to find concentration, and then that solution, once you find its concentration, you use it to do another lab which has nothing to do with acids and bases. So this can be the first step in something else. So often when you get to university, your lab periods are 3 hours because you might have to do this and then something else as well, okay? So this is an important type of procedure. That's something that you haven't done before, that we're going to do again in grade 12. So we're going to do a bunch of different kinds of examples, and in the end, it's going to be more sort of what your lab will look like. So what we're going to do, at the top of our burettes, it actually says 0 milliliters, which doesn't really make any sense. So you're going to fill it up. On your lab sheet, it says till 5 milliliters, but it doesn't really matter. You just don't want it to overflow. So you're going to fill it up with acid. It's not going to be, actually I should use yellow. It's not going to be blue. Yellow and an acid, that's okay. And so you're going to write down the volume, and you're going to write down whatever it is. 4 milliliters, 5 milliliters, whatever your burette says. But you'll be like, that doesn't make any sense at all because it's obviously full. That's not 4 milliliters. But we don't care about where it starts. You're just going to write it down, whatever it says. Then, partner A is going to work the stopper. Partner B is going to swirl, swirl, swirl. And then the color will change and you'll stop the reaction. So, what would we call this? Let's say you fill it up to 3. Okay, then reaction happens. And some of the acid gets used up. Your final volume will be 20. And again, you'll be like, there's way more than 20 in there, but that's where it will be, the little meniscus. It'll be at 20. What we care about is how much was added. So if we started at 3 and ended at 20, how much acid was added? 17. Just take the difference, yes? So these burettes are set up to help you. You put it in, write down what it says. We don't care, write it down what it says. Do the swirl, swirl, swirl. The stuff goes through. You get to end point, and then you stop, and all you have to do is subtract and find the difference. So then you would refill this with whatever. Ours happens to be a base. An indicator, and start again. But this time, you don't have to go back up to here because we don't care. You can go and say, okay, I've got 20 milliliters. That's my initial. And you know now, okay, around 17. If you got more color change than you wanted, then maybe around 15 milliliters, you could start to go slowly. Okay? So the burette is really, really precise, and that's meant to help you. Okay? So how does doing a titration help us calculate unknown concentrations? So the point in titration, when a solution is neutralized is called equivalence point, which equivalence means the same. So The moles of added solution are stoichiometrically equal to the moles of standard solution, or the moles of acid and base are the same or equal. So you can predict mathematically on a paper and pencil which we're going to do on here, where this should occur, like what volume. But then when you do the visual change during, or pH, digital pH, during an actual procedure, then that we call the endpoint. So equivalence point and endpoint ideally should be really close together. So sometimes students are like, Ms. Todd, seriously, we have to learn these words? Yes. So it's kind of like theoretical yield and actual yield. Do you want 100% yield? Yes. Do we always get that? Well, maybe not. So mathematically, predicting where the moles of acid and base are equal is called equivalence point. And then when you observe where neutralization occurs, that's called the endpoint. So the endpoint tells us equivalence point has been reached. So if you choose to do this qualitatively only, like an indicator like we're going to do, then you might get a tiny discrepancy. Okay. So for grade 11, the math that we're going to do is determine when the moles of acid are equal to the moles of base, or equivalence point. And so this formula looks almost like the dilution formula from yesterday. So CAVA equals CBVB, because moles is concentration times volume. This formula is a tiny bit different and sort of easier to use, because unlike yesterday where you kind of had to decide which is the 1 and which is the 2, when you do this formula, A stands for acid and B stands for base. So the acid information goes on this side and the base information goes on that side. Okay? So we do still need to consider stoic. But the good news is in grade 11, we're going to focus on strong acids and strong bases, okay? So how many protons are accepted by the base? How many moles of protons are donated by the acid? We're going to keep it simple. We're going to count. So I'll give you the formula of the acid and the formula of the base, and you have to look how many H's are there and how many OH's. So counting the number of hydrogens for the acid and hydroxides for the base. Okay, so we're going to do a simple example, then one where we have to, then it's not going to be 1-to-1, and then we'll do a titration example. Okay? So 13.84 milliliters of hydrochloric acid just neutralized 25 milliliters of 0.1 molar solution of sodium hydroxide. What is the concentration of the HCl? So again, this time, instead of it just being initially a strong concentration and then finally something more diluted or weaker like the dilution formula, you're given information about the acid and then information about the base. So normally And acid is obvious because it'll say the word acid, hydrochloric acid, sulfuric acid. What's another common one? Phosphoric acid, okay? Then the base, it doesn't say the solution of sodium hydroxide is basic or whatever. So yes, you do need to remember that hydroxide is a base. But even if you have a bit of a brain blip for a second, the acid should use the word acid, okay? So hopefully then you're like, okay, well, the other solution has to be the base. So it says 13.84 milliliters of hydrochloric acid. For this one, I do recommend that you write out what you know and what you don't so that you have acid and you have base. So I would even do it in columns. Just neutralize 25 milliliters of the hydroxide solution. So the base is 25. Moles per liter is concentration. Even if you forget, then if you go to read this, what's the concentration of the HCl, which is the acid? That means this concentration has to be the base, okay? So yes. Yes, and B stands for base. Okay, so in order to pay attention to stoichiometry, because the definition is stoichiometrically when the moles of acid are equal to the moles of base, what you can do, and I recommend that you write it down, how many H's does hydrochloric acid have? 1. Sodium hydroxide, it doesn't give you the formula here. They're both 1 and 1. So even though there's only ones, I know that's not going to impact our math, right? Multiplying or dividing by 1 doesn't change anything. But now we have taken it into account, okay? So they're the same. So moles of acid equal to moles of base. And then I'm going to write the ones in. Again, I realize that's not going to change anything. So H's are for the acid side. So write it on the acid side. OH's are for the base side. So write it on the base side. Okay? And then if it's not 1, like the next example, we're going to do H2SO4, then you can take into account the 2 when you do your math. Similar to yesterday, you might just not even need to show the divide by 1,000 to change it into liters. You can if you want to. You can write it in your data. You can write it right in the formula. Either of those is fine. I'll show all my work. You could even do this as one step if you have a good relationship with your calculator, and I would accept that. If you are a dimensional analysis kind of person, the liters cancel out. So now to isolate Ca, we're going to divide by the liters, which gives us in the end moles per liter. Are those the units for concentration? They sure are. Okay? And then just again, round appropriately, 2 decimal places, 3 decimal places. I don't really care. Okay. So now, this time, what volume of 0.45 molar H2SO4? So this time, we've got, what's the volume of the acid? Even if you forget what's an acid and a base, as long as you put the correct volume and concentration together, that really is all that matters. But one of them you have to count the H's, and then you should know that acids have H's, so it does all kind of go together. So now this time, how many hydrogens are there in H2SO4? 2. Whereas on the base side, we have 15 milliliters, 0.6 moles per liter. How many OHs? 1. So again, now that is going to impact our answer. So that's the stoichiometry part of it. So 2 H's. You have to write a 2 on the acid side. 1 OH. You have to write the 1 on the base side. There is a variety of ways you can solve this. So again, you can, and similar with the other example as well, if you're the kind of person who likes to rearrange the formula before you plug the numbers in, you can do that. Technically, you could do this all as one step as well, except you have to make sure that, let's say you're going to put it all in your calculator, you would do this first, yes? But then you would have to make sure you multiply 2 times 0.45 before you divide. So then you would have to use brackets. So it's kind of up to you how you want to solve this, okay? You could do as much of the multiplying before you start dividing and leave them on the same side if you want. And then you might be less of a victim to calculator error, okay? So now it's just straight up isolating. We want to get VA by itself. We're going to divide. Okay, so similar to yesterday, if it's just a paper and pencil task, it doesn't really say, then you can just leave it as liters. If you had to do something with this, kind of like we did yesterday in the lab part, then in order to measure, you would need milliliters. Our graduated cylinder, the burette, is in milliliters. But this is fine. Sometimes, again, I might want you to change it to milliliters to get an extra mark, but it would be very specific. What volume in liters or milliliters or whatever. Okay? And then this last example is more like a lab, okay? So a titration is completed using a 10 milliliter sample of hydrochloric acid with an unknown concentration and a solution of 0.1 mole per liter solution of sodium hydroxide. The following chart is the data of the 3 trials. And then in part A, it says volume of base added. So these questions can be a little bit tricky, but you can read the information you're given to help you. So we're going to calculate the volume of base that's added. So each of these trials has an initial volume and a final volume. How do you find the volume added? You just subtract. And you can just write your answer in the chart if you like. Same thing when you do the lab after lunch. You can just write your answer in the chart. So these answers are all pretty close together. That should be true. Just as an aside for when you do your lab later, again, when you use a burette, you don't have to go back to the original initial. So 0.1 to 12.52. Now this final volume becomes the initial for the next trial. Same thing here, 24.98, that becomes the new initial. So then you don't have to add stuff to the burette every time. Only if you use so much that you have to run out, but that's not going to happen with us in our lab, okay? Now, technically, this is a bad chart. Oh, it does say all volumes in milliliters. So you have to check and make sure that that is there, or you would have to write milliliters each time just to make sure that you know what you're talking about. Okay? So that's part A. Part B, calculate the average. So again, we're always at least 3 trials. Sometimes if you have a super crappy trial, like it gets really, really pea yellow, then some people will even do 4 and then ignore the crappy trial. Hopefully that shouldn't happen with you guys. But so again, show your work or not. And when you do an average, your answer should be close to the 3. They're not very far apart. So some calculators, you need to do 12.42 plus 12.46 plus 12.52, then push equals, and then divide. Okay? Actually, I won't round that much. Okay, so my average is pretty close. So really, you could do all of this, doing the subtracting, finding the average without even reading the question. But then part C, it says, using the average volume, calculate the unknown concentration of acid. That's where you really need to start to pay attention, okay? So we're finding the acid. That's what it says. Okay, so now I need to go back and figure out how much acid did we use. A titration is completed using, oh, there it is, 10 milliliters. Change it into liters. It's up to you if you want to do the stoich now. It says hydrochloric acid, HCl, which has an H count of 1. You're titrating that with a solution that's 0.1. Of sodium hydroxide, so its OH count, also 1. So isn't that nice? It's going to make our life easy. And then, what's the volume of the base? It does say here, using the average. It says here, volume of base, right? Okay, so you want to use the average. Sorry, I'm squishing. Sorry, I'm totally running out of room. Divide by 0.01. And the homework questions from the textbook are listed on the note as well.